Hello viewers, good morning. Professor T. Anoja here. Today I am going to present a new video on a very important topic, solution of Schrodinger wave equation. The following points will be discussed. For clarity and simplicity, I have divided the whole subject into several points noted here. Introduction. The Schrodinger wave equation can be exactly solved only for few cases, like a particle in a one-dimensional box or a three-dimensional box, one-dimensional simple harmonic oscillator, rigid rotor, or hydrogen-like atom. For particle in 1D box, some assumptions are like this. A box of edge A is hydrogen. The box is bounded by walls of infinite height, so that tiny particle of mass m is really moving inside the box, and it can never be found outside the box. The following are the limitations. Wave function describing the particle will be 0, where x equal to 0, less than 0, equal to a or more than a. But the wave function will not be 0, where x is greater than 0 or less than a. It means the particle will always remain within the box. It can never be found outside. And one more assumption, inside the box, the potential energy is supposed to be 0 because there is no potential barrier. At each and every point, potential energy is the same. On the walls and outside the walls, potential energy is infinite. The particle can never cross the walls. Here the same thing is described by a hand-drawn diagram. V is 0 inside, infinite on the walls, outside the walls. Particle of mass m is moving inside. Now we will write Schrodinger wave equation for this particle moving in one direction. D square psi over dx square plus 8 pi square m over h square t minus v I x equal to 0. What we will do in this equation, we will remove v because v is 0. Secondly, we will replace the constant terms 8 pi square m h square e by a single symbol k square. Thus, we have a second order ordinary differential equation, equation number 2. We have to solve this equation. If we solve this equation, more than one solutions are obtainable. One very simple solution is wave function psi x equal to a cos kx plus b sin kx. Here both k and b are arbitrary constants. We will have to evaluate these constants. Now, how to evaluate the arbitrary constants? We will apply boundary conditions. What is the boundary condition? As I told earlier, on the walls and outside the walls, wave function psi x is 0. It means a cos kx plus b cos sin kx must be equal to 0. This is possible only if we assume a is 0. Why a is 0? Because the angle is 0 degree or 180 degree. In both situations, cos kx cannot be 0. So in order to put first term equal to 0, a must be 0. Sin 0 and sin 180 both are 0. Therefore, b need not be 0. So out of those two constants, a is 0, b is non-zero. Therefore, wave function psi x equal to b sin kx. Similarly, b sin kx equal to b sin ka. It means sin k equal to 0. It means ka equal to n pi or k equal to n pi over a. Thus, we have evaluated k square, which is equivalent to 8 pi square me upon h square, and this is n square pi square over a square. We have derived the energy equation, very important equation, energy equation. Energy depends on two terms, quantum number n and edge a. Thus, we have evaluated the wave function psi n x equal to b sine n pi x over a, where n is an integer 1, 2, 3. Note that we have not included 0 because if we include 0, then psi x will become 0 and inside the particle will not be absent at any point. The wave function must be continuous. So we are constrained to eliminate 0. Energy of quantum states. We have derived the equation n square pi square over a square equal to 8 pi square me upon h square. It means E equal to n square h square upon 8 ma square. It means energy depends on two things. It is proportional to square of quantum number a n, and it is inversely proportional to the edge a square. A very important inference of this equation is energy states are not continuous, they are discrete and quantized in units of n square. If we take very large box A approaching infinity, energy states will no longer remain quantized. Instead, they merge together to form a continuum. Now we have to evaluate the normalization constant B. Total probability of finding the particle within the box, that is between limits x to 0, x to a, must be 1. Using this concept given by M. Max Born, we have evaluated the constant B, normalization constant, is equal to under root 2 upon A. Therefore, we can now write the normalized wave function psi n equal to under root 2 upon A sin n pi x over A. Origin of quantization. You see, in this case, quantization has originated naturally by applying the boundary conditions noted here. In Planck's formulation of energy E equal to nhf, n was introduced from outside on ad hoc basis. Similarly, in Bohr's model, u equal to nh upon 2 pi, n was introduced outside on ad hoc basis. But here in 1D box problem, n appears naturally. Graphical display of the wave function and the corresponding probability function. You see very clearly this graph shows wave function psi versus x. There is no node for quantum number 1, one node for quantum number 2, two nodes for quantum number 3, four nodes for quantum number 4, three nodes for quantum number 4. On the side graph, we have taken square of wave function. You see beauty of this second graph. Whereas in the first graph, where we have plotted wave function against x, amplitude is both plus and minus. But in the probability function, it is only plus. And the energy states are not quantized. They are in the ratio 1, 4, 9, 16, etc. So some more points about graphical display. The graph can be understood by applying these concepts. The nodal points are those points where the amplitude becomes 0, and all values where wavelength equal to 2a upon n become nodal point. Here in this graph, we have done a numerical problem. Energy states have been calculated. They are not continuous, they are discrete, they are not evenly distributed, they are unevenly distributed. So the most important thing is, for one-dimensional box, microscopic particle have quantized energy states. Again, in this numerical, we have calculated for microscopic particle. For a particle which is not microscopic, which is macroscopic, we find that the quantum number n becomes 3 into 10 to the power 30. Fantastically high value of quantum number, unimaginable, hence invalid. It means the concept of quantization applies only for very small particle moving along very small box, like chemical bonds. What will happen if the walls of 1D box are suddenly removed? then the particle energy state will not be quantized. They will become continuous. 0 point energy. When the particle is in its quantum state 1, its energy is not 0. It is always n square h square upon 8 ma square. So the difference in energy from n equal to 0 assumingly and n equal to 1 is called ZP 0 point energy. It means the particle will never come to rest even if the temperature is brought down to 0 Kelvin. This being so, the position of the particle cannot be precisely known. There always exists uncertainty, delta x. Likewise, the energy value will not be exact. There will always be some uncertainty because we will have to determine only the expectation value. The meaning is Heisenberg uncertainty principle is applicable. Now we take up a three-dimensional box of edge A. We will write Schrodinger wave equation in 3 dimensions. Then what we will do, we will first resolve the wave function psi into 3 components, x, y, and z, each depending on single variable. Likewise, equation 13 can be broken down into 3 separate equations, written over here as equation 15. It means by substitution, equation 15 has been substituted into equation 13 and divided throughout by 8 pi square m upon h square x, y, z to give equation 16. Equation 16 has 4 different terms. Terms first, second, third. They depend on one variable each, x or y or z. Term 4, E, is a total energy. It is sum of the 3 components Ex, Ey, Ez. Likewise, we can write the wave functions, 3 separate wave function equations, equation 19. You see, just like 1D box problem, here energy Ex, Ey, Ez, they depends on n square upon a square. And total energy depends on the square of the quantum numbers taken divided by h square multiplied by h square divided by 8ab square. Degeneracy of eigenstates. Degeneracy means more than one states having the same energy. Here I have noted one problem. Our energy 14 unit, Nx, Ny, and Z equal to 6 different combinations are possible. 6-fold degeneracy, this is called. Here I have tabulated degeneracy is not possible for all energy values. For example, it is possible for 6 or 9 or 14 units, but not for 3 or 12 units.